Hey Ram friends, welcome to Bharat Marg. I'm so happy to be here, friends, with you all. And here is Ved Kaila ji, Ved Kaila ji. Okay, and we are so happy to have Ved Kaila ji with us. And friends, today we are going to discuss about welcome, sir, for your thank you for your service for our children. And friends, you know what? Today we are going to learn about the introduction to functions on the day two from the experienced teacher, master himself. So just learn our you जाने के पहले friends, please make sure to like the video, comment on the video, share the video with as many people as you can. क्योंकि हमारा एक ही मकसद है कि अपने सनातनी बच्चों को जितना भी मदद हो जाए वो करने के लिए ही हम काम कर रहे हैं. तो please make sure to subscribe the channel Bharat Marg if you didn't already, and press the notification bell to stay connected with us, okay, so that anytime we go live you get informed. Also friends, we are involved in many good causes like Gau Seva, Gaudan, Anna Seva, Annadan, and more, and Sanskrit teaching. Okay, you are going to have a class now for learning Samaskritam from Bhagavad Gita. So a lot of things are happening, so stay connected with us. And also we do Annadan, Godan, Go Seva, and sending one dharmic message every day in the language of your choice, which goes around the world. If you are interested, you can WhatsApp to us for more detail, and you can support us by sharing this video, as well as friends, by donating to us. We'll highly appreciate it, okay, because we need your support. Okay, and here is Ved Kaila ji. Welcome, sir.
Welcome. Thank you so much. Welcome, everybody. So today is our day 2 of Introduction to Functions in Summer 2024. We already shared this course summary with you last time. You can review this. The agenda for today is the language of functions, utility of learning functions, restrictions of domain and range, evaluating value of a function, glimpse of parent functions, and if possible also key characteristics of functions and tools to evaluate and graph functions. Language of functions. As you know, every environment has its own language. Schools have their own, hospitals their own, courts their own. Like if you go to a hospital, they talk in terms of a doctor, nurse, ward, patient, prescription, pharmacy. Similarly, in the world of maths and science, there exists a special set of keywords and also special symbols. We have already seen some keywords like function, domain, range, restriction, etc. And we will see more going forward. After we get familiar with such words and symbols, then we can communicate within our community in very brief and precise manner. And to get familiar with these terms, I have provided you the links wherein there are symbols for maths like equal to, less than, greater than, and all that, and also symbols of set theory. So give you a glimpse, math symbols, they look like this. We will be mostly using equal to sign and not equal to sign, greater than or less than, also greater than or equal to and less than equal to, and some more. Similarly, in set theory, we talk in terms of a set, which is a collection of elements, and we talk of so many other things. For example, if you draw a vertical line, it means such that. So wherever you have to write such that, you can abbreviate it by a vertical line. And as we go forward, you will see that making our sentences small can make it easier for us to understand a topic. The downside is that people who don't know these symbols, they just get confused. So before you go much further in this course, you need to understand these symbols. Otherwise, just like a newcomer to a hospital doesn't get any message when doctors and nurses are talking to each other in their own language, and the visitors can get confused. So if you want to be on the top of things, you must know the language. Now, why do we learn functions at all? This is something you must understand before we proceed. Now, in our real life, lot of parameters depend on other parameters. And knowledge of functions helps us to understand such dependencies, make predictions, develop models, and do optimization, use tools to automate graphing and analyzing data. You will understand the meaning of all this as we move forward. Right now, some of this might look very cryptic to you. Applications of functions are found in many fields like sales, finance, economics, music, engineering, medicine, and anywhere and everywhere you can think of. For example, you hear things like buy two, get one free, or buy one, get second of the same type at half the price. All this meant to mold customer behavior. So you can think of this as a mixture of mathematics and psychology and sociology. Similarly, you might have seen that every day stock prices change minute to minute. The people who deal in them, they need to know what is the trend, whether a price of a stock is going up, going down, where it is likely to be tomorrow. Economics people want to understand the relationship between supply and demand. For example, in COVID times, the initially the masks were very expensive because the supply was very limited. So those who came in early to manufacture, they made a lot of money. A lot of other manufacturers jumped in. The supply increased, the price fell, the demand increased. How these things will play out can be predicted if you understand the relationships, and if you have created some models, and if you can do some automation using tools. You don't have to keep scratching your head or wait for things to happen. You can predict, and those who can predict, they derive the advantage. Therefore, knowledge of functions helps us in various ways to move towards a better future. Now, one of the word I used was modeling. Functions are useful because they enable us to model real world problems and visualize them graphically and compute their values using tools like computers. As an example, suppose you want to find the cost of setting up a rectangular form. The cost will obviously depend upon the form area and also on its perimeter. So if the form is L meters long and W meters wide, and say it costs $9 per square meter to dig it up and make the area ready, and if it costs $3 per meter to make its boundary wall, the boundary wall length will be 2 times length and 2 times width. The overall cost, let us write that as C, can be written as this expression. Overall cost C is a function of length and width, such that 9 times the area, which is the length multiplied by width, plus 3 times the perimeter, which is 2L plus 2W. This is a formula to model the cost of creating this farm. You can call it a formula, you can call it a function, you can call it a relationship, you can call it a dependency, and this cost depends upon two independent variables, length and width. Now that we have come up with this formula, we can use this formula, fit this formula in a computer, where whenever we give a value of L and W, it will quickly give us the cost. This is called a model. Now this, I said we can compute the cost, but computing the cost is not enough. We can optimize the cost, minimize the cost, if we know how the length and width affect the cost. So not only can we compute, not only can we create a model by creating this formula, we can feed this formula into a graphic application and see the graph and get an idea at a glance visually. But we can also use this formula in a computer and calculate the costs, and we can use other tools to minimize the cost, which is called optimization. And modeling is one reason why functions are so important. Whenever we make models, or whenever we deal with real world entities like numbers or weight or distance or temperature, there are some logical restrictions. For example, the number of students in a class has to be greater than 0 and has to be an integral number. It can be 5, it can be 10, it can be 7, but it cannot be 2.35. 2.35 is a decimal number or a fractional number, which are called real numbers. Whereas 1, 2, 3, 4 or 53 or minus 27, they are integral numbers. So some quantities in real life are integral quantities and some are real numbers. Now let's see an example about restrictions. With what speed will a coin dropped from CN Tower, which has a height of 553 meters, hit the earth? So from physics we know that after falling a distance x, the speed will be v equal to square root of 2 times g times x, where g is 9.81 meters per second per second. Now in this case, the stone can travel a distance of 0, it can travel a distance of 553 meters when it hits the earth, or any real number in between. So we specify the domain like this. We put a curly brace on the left, curly brace on the right, starting curly brace, ending curly brace. In between, we write X is a set of, which is a symbol of set theory. X is a member of real numbers, means it can be 25.3 or something like that, such that vertical line means such that X has to be greater than or equal to 0 and has to be less than or equal to 553. So now instead of writing such a long sentence, we can use these few characters which are easy to read and also easy to be interpreted by computers. Computers cannot understand when you write a language like X is a real number such that it is greater and all that. Computers will not understand that. But computers can understand this cryptic language, and therefore we need to understand this language. This is how we define domain, range, or restriction in case of this particular example. Next, the maximum speed is reached when the coin has traveled maximum distance or hits the earth, which can be calculated using this formula given above, which comes to 104 meters per second. So at the time of start, the speed is 0. When it hits the earth, the speed is 104 meters per second. In between, the speed is between 0 and 104. So we specified the range like this, again between the curly braces, which reads as V is a real number such that it is greater than or equal to 0 and less than or equal to 104. Now some functions use discrete data. For example, population for various years may be given like this in millions: 2001 2 million, 2002 2.1 million, 2003 2.4 million. Now you have a year 2001, you have a year 2002, you cannot have a year 2001.3. So this is a discrete data. There are points, not a continuous curve. So when plotted, these such curves will show up as dots. Whereas other functions are continuous. Example would be of continuous function will be height of a tree versus its age. As the age of the tree increases, the height of the tree increases. That is continuous function. Whereas this population function is a discrete function. Yet other functions have some jumps or holes. So this is a discrete function where you have certain points. And by the way, when I have shown this graph on the left, I have given a link where you can see how I made the graph and how I described the restrictions in that graph to get this kind of graph. Now it is often useful not only to come up with a formula or a model, quantitative model, but also do graphical design like this. This function shows some strange lines, like when the value of the independent variable or x is less than 0, the value is minus 1. Value of the function is minus 1 all through. But when the value of the independent variable becomes 0, then the value of the dependent variable y becomes 0, which is shown by a black dot. The difference between a solid dot and a hollow dot is that the point of the hollow dot is not included in that lower line, whereas the solid dot is included in the curved line. Similarly, when the value of independent variable x is 2, the value of the dependent variable y is 1, not 2, because the point 2, 2 does not lie on this curved line, but it lies on a horizontal line here. So this solid dot and a hollow dot are used to denote less than or less than equal to. This you will understand better when you click on this graph. So let me click it here. So you can see as I move from left to right, this point shows some jumps. There is a jump here and jump here. And on the left, you can see I have put some restrictions like less than, equal to. When we say less than equal to or greater than equal to, the point lies on that point on that curve. Whereas when we say that less than, that means the point does not reach. For example, the very first description here is fx equal to minus 3 less than x less than 0. So x less than 0 means as long as x is less than 0, the value is minus 1. But at x equal to 0, the value is defined by the next condition. So we will learn in one separate session, or you should learn the capability of making graphs from the formulas and vice versa. This is another example. So income tax is charged based on annual income like this. If income is less than or equal to 10,000, the tax is 0, which is depicted by the first part of the line. If the income is greater than 10,000 and less than 20,000, then the tax is 20% of the income which is greater than 10,000. That means tax is charged on income, on that part of income which is greater than 10,000. Whereas when the income is greater than 20,000, then the tax is 30% on the income which exceeds 20,000. And this, whatever story I am telling here, can be written mathematically by this description below, function written here below. And you can see this simulation by clicking this link. So as you move forward, you need to understand this language. Otherwise, you can write long descriptions which cannot be understood by computers and therefore are not of much use. So a little more about language of sets. As I said, we use curly braces to define or specify what we are talking about. The symbol is a member of, it looks like this. Vertical line means such that less than equal to, greater than equal to, not equal to. It is good to get familiar with such symbols and language, and it requires practice. If you get confused on the first reading, do not get frustrated because everybody has to go through that path. Learning any language is not easy. The first language that you learned when you were very young child took you several years. The next language that you learned in school took you a couple of months. So don't be surprised if this language, basics of this language takes you a couple of days. Now evaluating value of a function. Now it is good to make a formula, but what is the use of a formula if you can not use it? So here is a example where a apple cost $1.50 each. So to find the cost of Q apples, we come up with this formula. Amount of the money to pay depends upon quantity equal to 1.50 multiplied by quantity. So if you want to know how much to cost, how much is the cost for 4 apples, you just put 4 instead of Q and you compute this value to be $6. This is called evaluating a function. Now this is a very simple function, but there are some functions require a lot of calculations. And as you might be aware, applications like Excel and Google Sheets have large number of built-in functions where you can quickly plug in the parameter values and get the results. You can also evaluate a function using a graph. Like in this graph, when the independent variable x, in this case q, which is 4 apples, you want to find how much is the cost, you draw a vertical line like a blue line here, find out where it hits the curve. At that point of intersection, you draw a horizontal line and find out where it hits the y-axis, and you can say that the amount required is $6. Now in this case, the curve was very simple, so the situation was simple. Sometimes it can be pretty complex. Now, there are too many kinds of functions. To make sense of any real life function, you have to understand some basic functions. So, just as a cook needs to get familiar with the basic food ingredients, similarly, we need to understand characteristics of most basic, are often called parent functions. We can use the parent functions, transform them, mix them, and create our own meaningful model of real world problems. And that is one reason why functions are so useful. Now let us look at some parent functions. Now this is giving you just a glimpse of what parent functions are like. So this is a linear function, quadratic function, reciprocal function, step function, exponential function, logarithmic function, polynomial function, absolute value function, and so on. Now, Next, let us understand some other kind of functions. So far, we talked about functions which were one time functions. So, as I said, gave an example of a tree. If you plot how much is the height of a tree as it grows up, the height versus its age, you will see that only once in your lifetime, in the lifetime of the tree. Once the tree has become too old and fallen down, it is not going to grow up again to show you the same behavior again. But in certain other cases of functions which we call as cyclic functions, or you can call them repetitive functions, the same thing keeps on happening again and again. For example, if you are sitting in a Ferris wheel which is going around in a circular path over and over again, you are going over the same path in a repetitive manner. And this is an example of cyclic function. In case of trigonometric functions like sine of x or tangent of x or cosine of x, as shown here, the graph of sine x, this is an example of a repetitive functions. For example, whatever is the value of the function at x equal to 1 is the same value at x equal to 7.1. You can see the curve repeat itself after one complete cycle. So these functions also need to be understood. So next we will understand each of these parent functions in detail. Each of them requires probably a day or two to go over their characteristics. And later we will understand how to mold or transform any function to change its characteristics. For example, a linear function might look like this. By linear, we mean a straight line. A simple thing like a straight line has many properties. Looks very simple, but if you really want to understand it thoroughly, you have to look at it from various different perspectives. And linear functions are very common. The most common example that we have been repeating, the cost of apples, is a linear function. The more apples you buy, the more money you have to pay. That is something a child understands at a very young age. That if you have to buy two chocolates, you have to pay more money than buying one chocolate. So even though the child does not know what is a function, what is linear function, the child still understands the underlying meaning without knowing the name of the function that he is using. This is some other very simple linear functions. The red line is a vertical line and the blue line is a horizontal line. I have marked certain points on a vertical line like 3, -1, 3, 0, 3, 1, 3, 2. And as you can see, The x coordinate value of all those points is 3. As you move along the line, no matter where you are, the value of the x coordinate is 3. And if you give me any point with the x coordinate of 3, like 3, comma 20, I can tell you that point will lie on this line. So I can call this line as x equal to 3 because it is 3 units to the right of the vertical axis. Similarly, the blue line is 2 units below the x-axis, and all the points lying on it have their y value as minus 2. And if you give me any point whose y coordinate is minus 2, I can assure you that point will lie on this line. So I call that blue line as y equal to minus 2. And let me tell you, this vertical line and horizontal line that I am talking about, strictly speaking, they are not lines. A line extends in both directions indefinitely. These are line segments. They are part of a line. The lines with certain restrictions. So if I look at the simulation, you can see that here on the top left, x equal to 3 is a vertical line where the value of y is greater than minus 4 and less than 4. That means this line is restricted by this condition. Similarly, the blue line below, y equal to minus 2, has a restriction of where x is greater than minus 3 but less than 5. So it will be a good idea for you to look at these simulations and play with them to learn how to make your own graphic simulations. This is something which is hardly taught in schools, and knowledge of the skill of making graphs like this will give you an ace up your arm, strengthen your understanding, and make your understanding quicker. The next parent function that I am showing you is a quadratic or a parabolic function. A quadratic function shows up as a parabola. The word parabola just refers to a shape. The shape of your dish antenna is like a parabola. The reason it is like a parabola is that parabola helps us to concentrate the rays coming from a distance to a single point and enhances the strength of a signal at a specific point. So this is another application why you need to learn about parabola. It has a real life application of creating dish antennas. Now this parent parabola or a quadratic function is a basic quadratic function which opens upwards and has a standard shape. Now I am also showing on the left a list of points marked in red which are tabulated in a table. So you have an equation f equal to f of x equal to x square, which is the quadratic equation or a quadratic function. Below that you have a table of values at specific points showing 7 different points. And on the right you have a curve showing that function graphically. So if you look at that graph in a fraction of a second, you know that it is a quadratic function. So these are some basic, extremely basic parent functions. You need to understand many other parent functions which I listed above. For example, here, let's go over them again. Reciprocal function, step function, exponential function, logarithmic function, polynomial function, absolute value function, and after that, sinusoidal or trigonometric functions. So this should give you an idea about what functions are, why they are important, how to model them, and how to use technology or computers to evaluate their value and create graphs for quick visualization. So now let me show you. So instead of going into detailed discussion about various parent functions at this stage, I would rather take next 10 minutes to show you how you can create your own graphs. So this is an application where you can create an account of your own free and then create some graphs. So let me show you quickly how you can do that. This graph has a uh, x-axis which is marked in red, which has a y-axis which is marked in blue, and they are having graduations, and I can expand using, I can zoom in or zoom out. Now suppose I want to make a create a point on this. How do I do that? Or let me first tell you what are the contents of this graph. This graph is broken into 4 parts. this part shown in green, x greater than equal to 0, all the area in this green part has a x coordinate greater than 0. The area on the left side is x less than 0. The area above the horizontal axis is y greater than 0, and the area below the x-axis is y less than 0. This whole graph is broken into 4 parts. This is the first part, which is called quadrant 1, where x is greater than 0 and y is greater than 0. What does that mean? Any point lying in this graph will have their x coordinate greater than 0 or positive, and y coordinate also greater than 0. For example, if I make a point 3, 4, that point lies here at 3 and 4. Both are positive, so it lies here. Whereas if I say x less than 0 and y greater than 0, this is the second quadrant where x coordinates are negative but y coordinates are positive. So if I make a point like minus 3, 4, that would lie in this part. Next, if I make x less than 0 and y less than 0, that will be the third quadrant where both coordinates are negative. For example, minus 3, minus 4 would lie here. And similarly, I can say x greater than 0 but y less than 0. That will be the green quadrant, and any point which is positive x coordinate but negative y coordinate will lie there. So I can hide whatever I want to hide by clicking on the left. Now everything is gone. Now let's say I want to create a point, or we have already a point. Let me make this as 3, 4 and make this point. I want to give this point a name. Let me call that as a capital A, and let me give a label to that also as A, and let me give you another point which is equal to, let us say, 5, 2, and also let me label that as B. If I want to draw a line between A and B, probably I can do just this: A comma B, and I can say line. That creates a line. If I want to make a straight line, I can say, for example, y equal to x. This is a blue line. When x is 0, y is 0, x is 1, y is 1, and all that. But if I don't want this line to extend forever, I can put a condition. I can say, for example, minus 2 is less than equal to x and less than equal to 3. So now this line is a line segment. It is not a line but line segment which is restricted in this manner. I can make another line y equal to minus 2x. Let me put a restriction here. I don't want to see any value which is greater than 3 on the above side and minus 1. So I can say minus 1 less than equal to y less than equal to 3. So I can put restrictions on x or restrictions on y. I can also move these points, and as I move them, their value changes here on the left panel. So left panel is your algebraic view, the right panel is your graphical view. They are related. The x-axis and y-axis are marked, and you can change their markings from here. I can remove the grid altogether. See, all the markings are gone, 1, 2, 3, etc. are gone. I can go to reverse contrast to make a graph look different. So these are some of the ways in which you can use your knowledge of algebra on the left, geometry on the right, the tools provided by technology, in this case Desmos. You have many other tools. This is just one simplest of them, but getting familiar with any one of them at least will help you experiment your data. For example, if I want to make a circle of a radius 4, I can just write r equal to 4, and here is a circle. How simple is that? Uh, I can write any equations here. For example, I need not write y, I can write f of x equal to x to the power 2. So you get a parabola or quadratic equation. And you can change their colors. For example, this is violet color. I can from violet I can make it black. I can make it dashed. So you can manipulate, and this is how I have been using uh, to make graphs to show to you. But once they are made, they make the understanding simpler. For example, if you want to see what happens when I put a plus 1 here, you see the graph moved up. If I make minus 1 here, you see it went down. So you could experiment yourself using such technology. So this was all for today. I hope it is useful and should provide you a good solid foundation to learn this subject on your own and explore and utilize the technology as early as possible. All the best. Thank you very much. Jai Shri Krishna.
No, Jai Sri Ram, thank you, Ved Kaila ji, for coming and sharing your heart out and pouring your heart out. Okay, appreciate it. Thank you very much. ये इससे बच्चों के लिए बहुत बहुत फायदा हो चुका होगा, यही हमारा उम्मीद है कि आपका कोई भी सवाल है तो आप उधर कमेंट करके बोलें। इधर अपना व्हाट्सएप नंबर भी है, आप इसमें भी हमें संपर्क करके बोल सकते हैं। मैं इधर व्हाट्सएप नंबर लगाऊंगा। Okay, and if you have any question, feel free to contact us also. Okay, and जो भी वेद कैला जी के लिए भी सवाल है आप लगाइए, व्हाट्सअप किया तो भी उनको पहुंच जाएगा। कमेंट एरिया में भी आप लगा दें। और दोबारा दूसरा क्लास में दूसरा वीडियो में मिलेंगे, तब तक के लिए जय श्री राम। वेद कैला जी बहुत बहुत धन्यवाद, अप्रिशिएट। जय श्री कृष्ण।
Jai Shri Krishna.
थैंक यू टू यू सर।